Okay, I think we'll go ahead and get started. Thanks everyone for joining us for our EOL seminar. Our speaker today is Thomas Metzger Stefan Metzger. Sorry, many apologies. I was about to, whose PhD advisor's name was Thomas Foken, so that's why I crossed my wires in my head. Sorry. Stefan is currently with NEON here in Boulder, and he has a sort of a diverse scientific background. He did his PhD at the University of Bayreuth, finishing in 2013, and as part of his PhD, he pioneered the use of the world's smallest manned research aircraft, which you have to think about a little bit about to know what that is. Maybe he'll tell us, but it was a weight shift glider, and doing turbulence and eddy-covariance flux measurements from that. At NEON, he's been the lead of the eddy-covariance team, deploying something on the order of 50 towers around the U.S. And he's also developed mechanisms for dealing with representativity issues in these measurements, and supports several software tools that are widely used in the community. So we're very fortunate to have Stefan here today, and I'm looking forward to your talk. Thanks.
Thanks so much, Rich, for the introduction. This guy's working here now?
Yeah, turn it on.
Turn it on, all right. Thanks for the reminder. What about now? It's coming through?
Yeah.
Perfect. All right, thanks so much for the introduction. What I'm going to talk about today is from flux measurements to information, brief journey over land, air, and space. Sounds grand. Let's see what's behind it. A quick outline. Why do we want to use joint information? It's one of the topics we're going to address. We have many types of different measurements, how to reconcile them. We're going to follow up with that. How can we use then different types of measurements to unveil actual fields and processes in the atmosphere or surface based on observations? And in the end, a brief outlook how we could move this research forward. So without much further ado, let's get started. Why using joint information? What's the motivation behind that? Well, we all know that the Earth's surface is not static. It actually breathes. It exchanges energy, water, matter, carbon with the atmosphere. And on a larger scale, that leads to the cycling of water, energy, and carbon, as we just had. But that also has a lot of societal impacts. So if we think about, and I think there's a little sticky here, there's a whole web in how our society as we know it depends on availability of energy, food, health, ecosystem function, and essentially water resources that is all tied to these exchange mechanisms. Now, what we see recently happening is, and that's a report by the National Research Council, that we do have more and more extreme events and upward impacts of what we see as climate change. And what we do realize is that several of these processes, or where we're having our most trouble with, is that small spatial scales are not necessarily very well resolved in nowadays models. That our data still remains too sparse spatially to test some of the mechanisms, some of the underlying mechanisms that we might be interested in to address some of the most challenging societal questions and issues. And to also have the required data available 24/7 around the globe, essentially, at high spatial and temporal resolution. So that's observational data, not model data. That's with regard to shorter-term processes. Now let's look at longer-term processes. Here's a commentary, carbon metabolism of the terrestrial biosphere, where there's also the mention or the notion of scaling down and scaling up are both critical for an integrative understanding and program of carbon research and carbon cycling research, that we still facing issues with regard to different spatial and temporal domains, which mutually have the potential to constrain each other. and that we do have, here it says ground-based ground data, essentially observations, a lack of continuity of observations or space and time continuity to validate some of what we're currently modeling. Now, how, as observational researchers, would we go about remedying some of that? Or how do we start? Well, let's start in the field. That's essentially me in Taiwan in 2005. This was the first time that I got in touch with any of that micromet, deploying fog measurements in a tropical cloud fog forest in Taiwan. And you cross some precarious bridges, you deploy some more instruments, you finally get your tower up and running, and you get some good data and do some research within your specialization and report these results. Then you can go on, again still within your specialization. In this case, that's me doing research in Tibet. That was my master thesis. You might feel cold at some times in the high plateau, so you heat up water using the sun. You deploy your measurements. You might feel at times that it's not as comfortable as you're used to at home here, but then you see hardships of quite a different order of magnitude. So you carry on and complete your research and write your, in this case, master thesis. Now, then we can get sophisticated. So these were individual site deployments here. Now together with Sean, who's also in the audience, we went on using a more requirements-based value engineering type of approach by saying, okay, where do we get the biggest bang for the buck essentially here? This is value engineering in a nutshell. Here we still hold our own instruments, we deploy them, we figure out how in this case, infrared gas analyzer sampling systems can be optimized so as to improve frequency response close to an order of magnitude. And even the site moose was happy with that. Okay, so that's, again, we're getting very sophisticated now, but we're still within our own tiny field, our specialization. Now we can supersize it. And so that's essentially what I've been doing at NEON for the last 5 years. To deploy sophisticated, highly tuned instrumentation across a range of sites over the United States, across all sorts of bioclimates. We do, amongst others, have these flux measurements, but we also do have aquatic instrumentation, for example. We also do have aerosol sampling, lots of radiation measurement, rain gauges. And this is all based on the idea of value engineering. Now that we've supersized it, we can ask ourselves, within our own specialization, let's stick with the surface atmosphere exchange, with those fluxes, what's the science behind that? Okay, now we've managed to get some better spatiotemporal coverage, ecoregion coverage. Here in comparison, we're adding to AmeriFlux, an existing network of stations, and you see here, as color depicted, the various eco-climatic domains after Hargrove and Hoffman. And we do see that the value engineering was actually paying off by a strategic approach of choosing those sites. What we see is, with regard to detecting extreme events, that with 128 AmeriFlux sites, you can detect about 45% of the extreme events in this study. With only 1/3 of the number of NEON sites, you can detect still get 2/3 of that detection rate. So there's a lot of synergies to be had between these networks, and we're enriching. We're being enriching. Okay, again, that's our own specialization. We're talking fluxes now. What if we add another specialization to that, and we want to combine information among different areas or expertises? So now we're going into airborne, still flux measurements, but not at a tower anymore. Not at tower level, we're moving through space. And this was what Britt was referring to as the smallest manned research aircraft, at least at the time that I was working on. I'm not sure if that has changed. It's a weight-shift microlight aircraft. We do have a 5-hole wind probe for true airspeed, flow angles, inertial navigation system, For ground speed, attitude angle, so we combine those vectors and back out the wind speed, 3 wind speed with respect to Earth coordinates. We do have fast temperature sensing, infrared gas analyzer, and a data acquisition system that gives us a spatial resolution about 2.5 meters. Now, here's a tricky part about this aircraft that you can see here. This is the starting sequence of the aircraft, and you see how the pilot is pitching and rolling the wing. And there's a lot of studies been done in the past, and Don has substantially contributed to that as well. How do we actually correct for the vortices, the boundary layer around the aircraft? And since we have our air measurement system sitting down here, however, the vortice is mainly built out with respect to the airfoil. That can get kind of tricky. So instead of starting with flux measurements when I started my PhD, which is what I was kind of promised by my supervisor, I had to spend a couple of years figuring out how that wind measurement worked. And we got it done, but that was kind of a challenging part. So we did our due diligence. We're now in a different specialization here, early beginnings. We figure out that for this particular aircraft, which has a flex wing, so the wing compresses, and for that reason, the vortex around the wing is also modulated. So we figure out our original wind measurement, which you see here in gray, had all this modulation that was resulting from the degrees of freedom of the wind measurement with respect to the wing and the wing flexing itself. And I came up with a new methodology, how to correct for dynamic upwash, considering the actual lift coefficient or actual lift explicitly, and we get pretty darn close to an average of zero, mean zero vertical wind. Our second specialization here, further due diligence, we do intercomparisons with tower measurements. We figure out that the precision resolution is sufficient to do defensible flux measurements. And now we are ready to pack it up together with a centimeter measurement, go to China, send it off to China to do our first experimental campaign. While it's in transfer, the aircraft, we need to do some flight planning. So what we see here is essentially a map with the slope backed out, and trying to figure out within the performance envelope of the aircraft and the wind measurement system, what are routes within which we, on the one hand, are able to represent the diversity of the environment, but at the same time are flying within the performance requirements of the mission. We had to work a bit with the Chinese authorities to get that all confirmed. And then we're taking off, right? Can't be that hard. Going to Inner Mongolia. We have lots of data resources from remote sensing, classifications, on the ground cover classifications. So it should be really straightforward to just regionalize the flux over that catchment. Well, is it? Turned out that was my second headache during the PhD. So what essentially happened is that, see if we can get that kicked off, in terms of supersizing it. The first headache was that, all right, we have this footprint thing. So back at the tower, just to simplify it, we really only, for each observation that we're taking that we're calling a flux measurement or observation, we see a tiny snapshot of the surface of the area that we're interested in. So it's our footprint to grid representativeness. Then even if we can express individual grids, what is our grid to landscape representativeness on a larger level? Then how do these things change over time? And what are the process relationships? So if we want to get anything out of that to inform our predictive capacity, we need to get a better understanding of the functional response. So now, here was the headache. Now to break it down to two challenge questions that we're facing with regard to spatial heterogeneity. One is location bias. So we do know if we're only measuring in certain locations, we cannot assume, well, we should not assume, it is often readily assumed, that our measurement represents one scale up. So for example, merging with remote sensing data or model validation of numerical models. This here is a study by Chen et al. What they show is essentially, if we do have, this is still a tower, if we do have a tower measurement and we increase our area of interest relative to what the tower is actually measuring, we do get a location bias. And so if you have a MODIS pixel, 1 kilometer square, but you actually want to compare remote sensing parameterized flux to your observation, you might easily be in the order of 10 or several 10% bias just by doing that, just by making that assumption. And another interesting conundrum is with regard to energy imbalance. So in situ measured turbulent fluxes do not equal the net available radiation on the surface. We do see that, and that's a Paul Stoy's study, we do see that actually also scales with surface heterogeneity here expressed in form of the greenness variance. So we do see that for some of these challenges that are permeating science as it's currently being conducted, surface heterogeneity apparently plays a pretty big role. So on the one hand, we have this big castle of many specializations that are conducting their research together. So our castle in the field probably looks something more like that. We have a fully instrumented tower, tons of people on the ground doing surveys, 24/7 aircraft and satellite flying over. Now, the question is, on the one hand, we have all the sophisticated technology on the ground, and with the theories and assumptions, it enables us to have spatiotemporally more continuous coverage. But on the other hand, when these theories and assumptions differ among the different disciplines and among the different measurements, we're really still facing an uphill struggle to extract joint information among the different observations. So, to back out our motivation, challenges we are facing, extreme and severe weather causing loss of life, goods, and food supplies, and we're still struggling to forecast some of that and have early warning systems or reliable early warning systems. In particular, over non-uniform areas, our understanding of this aggregation process is limited, and that is quite relevant because a good portion of the human population is living in these non-uniform areas such as coastal zones, diverse urban areas, or they depend on mountain resources. So here's some questions that I suggest we ask ourselves. How to continuously and reliably deconvolve covariations in space and time that we observe? How do we address observational bias that's related to assumptions of surface homogeneity and stationarity? Then how do we make that work for our models? How do we bridge scales for simulating various disparate measurements into our models? And how can we use our joint observation or the joint information content among our observations to decipher the process among environmental compartments so that we can actually have mechanisms that are calibrated out of landscape process rather than laboratory processes under very defined and oftentimes constant conditions to inform the process in our models. All right. Now, from here we move on. We know what we're setting out to do. So how can we reconcile the different types of measurements? And I'm actually going to use that and take a sip of water here so I'm not running dry. Now let's look at a scope diagram, a scope of our task. We do have at least three categories of observations: ground-based, airborne, spaceborne. They complement each other in terms of coverage and also in terms of resolution, but they don't really fill the whole picture in terms of temporal scale and spatial scale. So to fill the whole picture and to really get to 24/7 globally, we do need some integrators such as Earth system models. And we do see they're working pretty good at many of the scales, but there's other scales for which an additional integrator or a simulation mechanism might be quite useful. And so what I propose to look at in the remainder of the seminar is that gray area that we see here at the shorter time and space scales. And how can we integrate observations, many of these observations, taking place in this space-time area. Okay, we've been talking about different measurements having different underlying theory and assumptions. Let's look at one of them as an example. So we do have a tower measurement. We've seen that the tower measurement does have a source area or a representative area, a flux footprint. If we do have, even at the same tower, different measurement level, that does have a different source area, and so forth. And what we actually see is that not only do we have a different area where our measured or observed plume intersects with the surface, but we do in fact have somewhat of a Lagrangian control volume that continuously changes over time with different turbulence properties, with different wind directions, and so forth. Now, what's depicted here as a Lagrangian control volume is not what we're supposed to do per our underlying model, per our theory. What we're supposed to do is to have a control volume, such as a box, easily put. And what we do measure in there is mainly three terms. The storage change, so enrichment or depletion of a scalar of interest in the box. Horizontal transport across the faces. And then the transport through the lid. And as long as we can measure all of these different terms, we use the mass balance equations and back out our net flux. It's as easy as that, right? Well, now here is what we actually do measure, what we can feasibly measure at this point. We do make quite a few assumptions, such as surface homogeneity, to name one of them, in general divergence-free flow. And we do measure only essentially along a tower column with regard to the storage exchange, and at a single point on the top of that lid to determine what is the net exchange, not the net exchange, sorry, the turbulent exchange over the lid. And all the other terms cancel out due to our assumptions. Now, we need to do a lot of tests to actually see whether our assumptions hold true if we want to be able to do this. At the same time, we've seen if we do that, then we're still facing these conundra or conundrums such as surface energy imbalance. So I was setting out to do that somewhat differently, to come up with a mapping operator between the Lagrangian and the Eulerian representation. This is where we're currently at, and I'm going to lead towards that now with the introduction of the environmental response function methodology. What really helped me to figure out that methodology were airborne flux measurements, which are really rich in information content over heterogeneous landscape, a much higher signal-to-noise ratio than what we oftentimes see from flux towers, which was really helpful in figuring out that method. So here, really simply put, linking flux measurements to surface properties. So if we're flying over a heterogeneous surface at different times, we do see different blended surface influences. And in the simplest of all equation systems, these are a linear combination or linear recombination, which was done a while ago, almost 20 years ago, by Chen et al. Now, if we take this to the next level and considering two principal steps, extracting the relationship between environmental drivers and responses. And drivers can be both surface drivers, they can be meteorological drivers, such as air temperature, humidity, and so forth. We can extract the process among them using technologies such as used by Tesla, Google, and so forth, data mining technologies, to infer these responses. And we're able to then have parametric relationships fitted against these responses. So it's really a response extraction from the landscape. And then we apply this knowledge to bridge scale gaps in space and time. Let's put this together. We have in situ measurements of turbulence statistics and meteorological drivers. We do instead of what's been done in the past, we apply time-frequency decomposition, which gives us a much higher spatial or temporal resolution of our observations. So we have a much larger sample size, and only that high sample size allows us to use some of these emergent technologies, such as deep learning. Then we do our source area modeling. We identify biophysical land surface drivers from footprint modeling. And eventually we extract the relationships using deep learning. And all of these steps together is the extraction component of environmental response, of the environmental response function, which we can then apply in a projection mode to get to a formal transfer between, in this case, a Lagrangian and a Eulerian representation of an observation. Now, let's look at it formally. So the situation that we find ourselves in is that we do have expensive response observations R, or comparatively response observations R, that are spatially or temporally sparse, such as flux measurements, comparatively sparse, compared to some of the driver observations, which are collectively cheap and dense, such as temperature from met stations, surface temperature from satellite, overpasses, and so forth. And then we can also throw in the mix whatever prose understanding we already have, such as advection dispersion modeling or flux gradient methodologies. And what the machine learning then helps us to do is to combine these information in an extraction step here. The extraction itself is sparse in the space-time domain. It's constrained through the expensive response expensive response observations. Now, once we've extracted the relationships, we can go into the projection mode, into the transfer function mode. And we do have the ERF projection here, which is then dense in the space-time domains through a transfer function in the in the collectively dense driver data sets. So with that, it yields the most complete approximation of the true responses across space and time that is possible from all the different information sources that we can get our hands on. And again, that can be observations, it can be functional or process understanding. There's nothing that we need to omit. And an example application, but really only an example, is the mass balance framework that we just looked at. There's many other application possibilities for this type of framework. Okay, now to summarize graphically, what we do have, we do perform our footprint modeling over coordinated observations of drivers and responses. You see here, we extract the response relationships, we map our virtual control volume, and then we formally, with our formal mass balance approach, we formally equate the mass balance over that control volume, and instead of a single observation, a single point in space or time that we had before, we now have a space-time distribution function that can be subset if wanted or if needed by different land covers or similar. And that can, here in the simplest way, there's already three entry points to inform numerical modeling. One is to parameterize either existing relationships against the extracted responses, to parameterize new relationships against the extracted responses and use those in numerical models, and or to perform formal data assimilation with the projected fields, or the projected results, distribution results of the projected fields. All right. Now, what that provides us in this case is we solve the mass balance equation. We're able to solve or approximate the mass balance equations much better than we originally were from a single tower. Instead of having flux observations that advect in a non-homogeneous fashion past our tower, we can sort out these drivers and responses and only subselect those projections that actually match, for example, our remote sensing footprint against which we want to compare it. So this is the theory behind it. To actually implement it, there's more required than coming up with the theory behind it. We do need the hardware and an experiment design, as we've been looking at, but then we also need certain catalysts to actually test and operationalize some of that. And one of that is software crossing traditional disciplinary boundaries. We're going to have a brief look at that, what I mean with that, in the upcoming slides. And we also, especially when working in larger teams, such as I also see here happening at NCAR, we do need a cross-coordination mechanism. And what we've been quite successful with, I think, in the past 1 to 2 years, is it's called an Agile method of development, where initially the heterogeneous group of, for example, engineers, scientists, stakeholders, and so forth, they agree on certain requirements, acceptance criteria, definition of done, then an original design is being derived. The design is being chopped up into responsibilities, individual responsibilities, and then we regularly meet and every 2 weeks essentially, and bring this back together. And so we apply this methodology to the science of environmental response function here. All right, it's going to be another sip for me. So now, let's see what's coming out of that. Unveiling the actual fields and processes. So what we do see here are time slices for applying environmental response function as a transfer function. Here for the volume projected heat storage exchange and the grid projected turbulent heat flux. And what you can see particularly well here in the turbulent heat flux, the source area of our measurement of the actual tower observation in this case is jumping around wildly. So every, in this case, half hour or hour is representing a very different surface patch. So wanting to compare that to always the same satellite grid pixel, it's going to be quite challenging and not really comparable. But if we're actually able to extract now the flux distributions or really distribution of pretty much anything that we're interested in over the same target area as another measurement that we want to marry it with, we're now able to do so. We can now add these different terms together, storage flux and turbulent flux, and come up with net surface atmosphere exchange, as we see here. And if we actually do that, there's some quite interesting characteristics that are springing out from the resulting probability density functions. So what you see here is the Gaussian-like curve in red here is the actual observation from the tower with the calculated random error. And what you see here in the black, not quite bell-shaped type of curve is the actual PDF over the target area in this case. And you see these long tails. See these long tails, and these long tails are systematically here, in this case, towards higher fluxes. What we also see is that with regard to the mean flux over an observation area or mean quantity over an observation area, the probability that our target area, the probability that our observation represents that is quite high, 94% probability. It's pretty good. We probably don't need not too much more there. However, with regard to the variation in the target area, for that time slice, we're getting down to 70%. And if we do this over and over again, this is just a single time slice, a single hour. If we do this over and over again, we do see a pattern that, yes, we can actually represent the mean quantity over, I think in this case, a 5 by 5 kilometer target area quite well. But we do see, that was one too early, we do see that the representativeness of the variation decreases rapidly. And so what that tells us, many of the surface atmosphere interaction processes are highly nonlinear. If we are not able to express our variation across a spatial domain properly, we're probably getting quite a few of these nonlinear interactions not quite right. And however, if we do use this type of protection mechanism, there's something else quite interesting coming out of that. as compared, this is over a month of data here at the WLEF Tall Tower in Wisconsin. What we do see coming out of that is that the tower measurement here, in this case, at around 20-30 watts per meter square for that study. This is the sensible heat flux. If we do compare that to continuous aggregation, so almost like an ogive analysis in space here, to a continuous aggregation in space. So this here is the side length of the aggregated area from 0 to 20 kilometer. We do see if we're aggregating over more space, initially we do have a rapid increase of the flux until it sort of tapers out. In this case for sensible heat flux, where we're reaching a plateau, and we've probably reached that landscape scale where inclusion of additional patterns now begin to cancel each other out. We're not seeing the effect of individual patches anymore. And this is even more evident here for the latent heat flux, where initially it's really jumpy if we're beginning to integrate over more surface patterns. And also this here begins to taper out and converge at a landscape scale of about 15 kilometer side length. And so if we think about that, this is where probably if we're calculating the energy balance, we are equating together observations with very different, that represent very different surface areas and have very different assumptions with regard to their representation of a volume versus a surface and so forth. So if we actually begin to reconcile some of these differences, we are probably able to address part of the systematic imbalance that we're currently facing. So this was the scientific part of it. Now we also want to be able, it's great to do that as a case study, but we might want to go further than that and want to also enable others to do similar studies and further develop it, continuous development. So what I, together with my team, came up with is the 84R family of R packages that includes these capabilities, among others. There's also standard flux processing capabilities built in there. And together with other existing and forthcoming packages, such as NEON MetScanner, or the Max Planck Institute also has a pretty nice packages for higher level processing. We really enable the community to come up with adjustable and extensible workflows in a single end-to-end environment and tool chain. It's not a one-way road. So the way that we're building this is that the software itself is community accessible, not only accessible, but also extensible. We're using this Dockerized platform for that. I've seen that RAF is also using that. There was a talk, Whales on Plane, which I found quite interesting. So we're using this Docker shipper containing system to build our software in, and then everybody can download this turnkey container, and it's working 100% reproducible on either a laptop, from everything from a laptop or a desktop to a cluster. So we have this actually deployed on high-performance computing as well. Here's what you see in the bottom right is that feedback loop. Now, initially I may be a user of that container, and of that software, but I do realize, there's actually I found something that I'd like to add that helped me. You can absolutely do that. You can contribute back to the software, and in its next iteration, it can include your feature and including your copyright, and you essentially have a mechanism to get your research out there and have other people use it as well. Here's just to show that despite its advanced capabilities, like what we've been talking about with regard to response functions, it is still comparable to standard flux processing software. So we did here intercomparison with oftentimes a frequently used software called eddy-pro, which is provided by one of the major sensor manufacturers, Lycor. And so in case you're interested in this kind of technical level, there's a paper in discussion right now into scientific model development. And what that mechanism really enabled us to kickstart is not just to finally do our regionalization of energy fluxes in Mongolia. This was the starting point. We also did NOx emissions over London by now, to name one example. VOC is following right now. Methane emission over Arctic permafrost. And methane emission from dairy. And there's several more that I just didn't have space to put on here. Now we have our case study. We have made it scalable by also sharing our recipes. How do we get there? Now we also want to be able to disseminate our data. And so that's something my team is doing via the NEON data portal with API capability. So in your code, it can be the system that we are providing, or your own code. You can directly tap into the download mechanisms. And we also do quite a few outreach activities. So one of that was to raise awareness of how, in particular with regard to undergraduate students, undergraduate graduate level students, how do we actually do these things? Why are these things interesting, important, and incentivize them? All right, so now we have supposedly a community that is interested. Now we also want to make sure that what we're doing is not just interoperable in this type of case studies or comparable, but maybe even globally. So there's other networks in the type of, or the line of research that we're doing, which is what you see here. And we actually came up with a mechanism together with these networks, how to come up with some of that so that our users can utilize all of our data together without having biases across different networks. This is one example where we've registered our first site with AmeriFlux to do exactly that. There's a poster that we recently shown, and it doesn't stop there. That brings us all the way back to the planning component. We do visit, NEON Airborne Remote Sensing does visit quite a few, does visit all of our close to 50 sites across the United States, but oftentimes there's partner sites co-located as well, or maybe future partner sites. And so one of the things that we've been doing is active outreach in identifying if we're flying these sites once to twice a year, which doesn't come cheap, is there any low-hanging fruits in the vicinity, either of AmeriFlux or other partners, LTR, and so forth, that are even already either already co-located or adjacent, where we could partner, team up, make sure that if we are flying, ground instrumentation is running as well, so we actually get a comprehensive data set out of which we can extract our joint information content. So now I'm starting to wrap up. That's the part where to go from here, right? Let's start with a brief summary. So we've been talking about why using joint information. We've been talking about understanding extreme and severe weather, and especially their aggregation mechanisms in non-uniform terrain. That we do have lots of individual sophisticated measurements, and they become more spatiotemporally continuous and available. But at the same time, de-convolving observational covariations in space and time is still pretty challenging with the tools that we have nowadays. Now, how can we use these different types of measurements together when assumptions among methods differ? Extraction of joint information becomes challenging. One way that I propose using the ERF, the response function approach, is to explicitly express and solve the assumptions underlying each individual measurement, and in that way maximize data use efficiency through catalyzing, complementing information content. And through the prose extraction, we get a calibration to the landscape as compared to a calibration to a synthetic experiment in a laboratory environment. Then unveiling the actual fields and processes. Through that, we get an unbiased, or maybe at least a less biased link to larger scale ESMs. We also create an assimilator for emergent data intensive observations. So we have a lot more isotopes measurements coming on. I learned a lot about LiDAR today here. Radiometry, remote sensing. And there's a lot of applications beyond these example observations that I've been showing today, the flux measurements, and that can go as far as using some of these methodologies for sensor correction, calibration, if there is a lot of covariations in some of the sensitivities of an instrument. Now, moving this forward, I've been mentioning earlier today in our discussions that the way that I can see this going forward is an integrated development of hardware, software, and experiment strategies against scientific requirements, against what is needed. Let's specify that, and we can build everything else is engineering. We can build it against that. And to that end, I do bring 3 ideas with me to get us thinking about what could be done outside the scope of flux measurements, or purely the approaches that we've currently seen. I've been learning a lot about the LAMMPS measurement today, so actually combining that with fast trace gas analyzers for different species, that could be a quite interesting undertaking. I think the benefit lies into eliminating the observer effect. We've been talking about upwash and the challenges of it, and you still don't get, even if you do a correction, you don't get completely rid of it. And to attain a certain spatial resolution. This is the one idea that is least developed in my mind. So I have to talk a lot more with you guys about budget considerations and similar. I heard, though, about Aristofly testing opportunities, so this is something I wanted to mention here. The other 2 value propositions that I have are much more fleshed out. I do actually have proposal drafts for that, and I'd still like to share and see if there's an opportunity for engagement. And so the next one is FLAME, flux landscape mapping using environmental response functions. The benefit is to operational bridge scales and representation of various observations and make them usable for models. We've been budgeting that together with close to 15 collaborators in the United States and the EU to about 1.5 million. And we're currently targeting DOE funding as well as NASA ROSES. And then the third one here is ALK, atmospheric emission location quantification for the oil and gas industry. We are currently in touch with representatives of the oil and gas industry to come up with an operational, order of magnitude more cost-efficient gas leak detection system using things like unmanned aerial systems, but also tower measurements. There was actually just recently an environmental defense fund challenge with regard to methane detection capabilities, and the Quanta who won that challenge, they actually located in Boulder. So we're in touch with them as well. They have the measurement capabilities, but they're what we could complement them with is some of this source area attribution and actually making sense of where that leak is and what's the magnitude. That's a bit cheaper, about $500,000, and we're targeting small business administration, SBIR and STDR programs, as well as the Environmental Defense Fund. And then there's ... So I'm looking forward to your ideas, and I'd be more than happy to discuss. That's all I have. And with that, I'm available to your questions.
Great. Thank you, Stefan. Thank you, Stefan. We have time for questions. If anyone from the audience has one. Ned? Oh, here, just...
So back to your environmental response function test with the big grids, and you were showing from a tower measurement that the footprint changes all the time, and so you're only sampling that heterogeneity at certain times of day. I presume that the footprint is larger versus smaller, and therefore you're training your response function based on a single piece of the atmosphere at that time and how the exchange is occurring through that. I'm just curious how you bring the time variation of the footprint analysis into to inform the relationships between that point measurement and that which would be the full
Right.
grid box.
Right. So the tricky part in that, the tricky part lies in sufficiently representing surface and atmosphere state space combinations, in the areas that you sample, as you mentioned, and then being able to translate that into similar high-dimensional state space combinations into areas that you might have only sampled a very few times, or potentially not at all. And we did various sensitivity analysis using multiple proxies of remote sensing land surface data products, as well as going as far as using WRF reanalysis data to supply atmospheric fields. And we came up with an uncertainty budget that was confirming that while we originally started with up to close to 100 different surface and atmosphere drivers that we map using footprint functionality to the observation on the tower, in most cases, 5 to 10 observational remote sensing and similar observational layers are sufficient to bring the uncertainty of projecting into areas that were not originally observed, but that have a similar state space combination as confirmed by these grids, to below 10%. Does it answer the question? Yeah.
Other questions? Yeah, just a follow-up to that. What sort of, over what period of time is the ERF trained? And can you say a little bit more about sort of, for myself and others who might not know, what the machine learning or deep learning part of this actually does?
Yeah. Sorry, and I guess I missed to answer that question to Ned as well. Like, what's the kind of data volume or size that goes in there? From about 10,000 observations that go into the machine learning, the algorithm is beginning to be robust under various settings or for various sites that we've seen so far. Now, the challenging question here is, how do I get 10,000 observations? And if I do that in the standard eddy-covariance manner, and I do half-hourly averages or hourly averages, you have to wait. You're probably getting into seasonal cycles and similar. So it gets much more challenging to extract any of that. And so that's where the time-frequency decomposition component is coming in. So using empirical mode decomposition or wavelet analysis, it allows us within a 1 minute, within a 1 hour time period to get up to 60 observations on a tower, or do the same in the space domain at 100 meter resolution for the aircraft. And in that way, without neglecting long wavelengths contributions to the flux. And in that way, we bump up our, not only the number of observations that we get, but we also decrease the blending effect of averaging over longer time or space domain. So it becomes, our observation becomes much more representative of, say, an individual patch of surface. So our signal to noise ratio goes up, and we did various sensitivity analysis against that as well. And 100 meter on aircraft, spatial resolutions at about 50 to 300 meter flight height, and down to a minute resolution tower is what's been working pretty well so far.
If you have another environmental response function question, you should ask it first.
Did you ever go back to your Mongolia data set where you had flux measurements at the ground and the aircraft and isolate and or test the environmental response function analysis with and without the aircraft to show the value of the aircraft in the spatial sampling and how it would affect the training of the system?
We didn't do that in Mongolia. We did do that in Wisconsin, though. Not between aircraft and tower, but between tall tower and normal tower. So we did use the WLEF tall tower, with which you have a much larger field of view. So it's not quite akin an aircraft, but sort of going into that direction. So we're measuring up to 400 meters on that tower, mostly 122 and 30 meters. And then a 10 to 20, 30 meter tower 15 kilometers away. And we've actually been doing the cross-validation. And our uncertainty budget was confirmed that we did get a bias that was less than 10%. And the bias was actually correctable. So the machine learning bias was correctable by a target domain, simple linear least squares calibration over the domain, without the knowledge of that separate site, I must say. So only based on the knowledge of what went into the method.
And that answered my question.
Oh.
One critical part for the data assimilation for such a new observation type would be how to characterize the observation error statistics, especially for the flux measurement. I would guess like the temporal error correlation would be large. And can you say a little bit about that? How you guys actually process how to compute or estimate the error statistics of such observations?
Absolutely. So we do have an uncertainty budget approach that I mentioned before. I've not yet been talking about the different components of it, so thanks a lot for the question. We do start from the sensor error, the input error that's simply coming from the different sensing elements. Then we look at uncertainties that are being contributed by different types of observation. So, for example, random and systematic sampling error of atmospheric turbulent observations. Adding to that, if we do use remote sensing data typically comes with quality criteria as well. So this factors in as another budget item. So a quality criterion, like a flag 3 to 1, is oftentimes associated with a bracket of uncertainty. Land surface temperature down to 0.05 kelvins, for example. There's another bracket, and then we go into the data analysis budget, where we propagate these things numerically and do a piecewise sector exclusion. So if we think of our target area as a square, we only use all data that is sourced from a wind direction that's coming from the northeast and project into all the other areas, into all the other 3 quadrants, and then compare that to the actual observations from these quadrants, and so forth. And then, so what happens, these error estimates, these individual components are being numerically combined using MCMC Bayesian cutoff method, and each projected cell has the combined error estimate supplied with it.
Okay, great. Thanks a lot. I suggest we stop there. We'll have just a few minutes if anyone has questions they'd like to ask following on. But otherwise, let's thank our speaker again.